Hi all, welcome back. So today we are going to discuss about the basically we have to understand the various type of timers to be required in embedded system. So here we will try to dive into different various type of timers to be used in embedded system. So all right. So in case of embedded system, timers is everywhere. So embedded system are real time and action must happen at a correct moment. Whenever we perform any action, is to be uh, uh, is to be initiated at a correct time. So here you can see central processing unit CPU only delay loops are the inaccurate. What's the cause to delay the loops? Inaccurate depends on compiler and optimization, like how uh, we are doing the optimization so and wasteful like CPU is busy waiting unnecessarily we put the wage busy some waiting time and unsafe blocking delays can miss events and deadlines. So of course, so this is important. So embedded system real time we already seen. So timer here you can see second bullet points. Precise timing and repeatability is important. And event generation without CPU load. Reliable time measurement for control and sensing. All right. So here you can see like embedded system is everywhere in automotives, robotics, industrial control, and IoT, Internet of Things. So wherever embedded system involved, of course timers to be like part of the embedded system. So so it is there. So now question is what's a timer? So timer is a hardware peripheral inside the microcontroller unit. So it counts clock pulse to the major time intervals. This is also called the time stamping. Generate periodic interrupts. This is called the time base. And generate waveforms. This is to be used in our motor control basically. Pulse width modulation (PWM) and measure frequency and pulse width input capture. Okay. So this is various form by which timer can be used and how we can timer uh, is there. So timer basically count the clock pulses. Okay. So what is the advantage? Key points actually. So hardware counting even while CPU executes the other task. So whenever CPU busy in other task, that time also hardware count the it keep on counting. So time is consistent even if CPU is busy. So that's important. So timer hardware building blocks like clock source, advanced peripheral bus, clock or advanced high performance bus, clock and external clock input. So real time clock, the RTC domain oscillator or low power timers. So there are various type of you can see register we are using actually in this. So real-time domain oscillator for low power timers where power required less. The Prescaler Register, this called in short form PSC, divides clock to form timer tick. So like whatever time is there, so it will be divided by something based on your need. Okay. Counter register, current count value increases or decreases, auto reload register, maximum count defines period, capture and compare register CCR, compare PWM and capture measurement. So here you can see Prescaler Register, slow down the timer clock, f tick is equal to f clock by PSC plus 1. So like that we can find out the frequency of ticking. So counter register counts every tick. So basically pre-scaler register slow down the timer clock and we get the frequency ticking. And how we can count the every tick using the counter register. So current timer roll. Okay. So auto reload register when CNT count register reaches auto reload register time and the timer overflows and repeats. Okay. So capture a compare register compare mode even when CNT equal to CCR and use in PWM toggling output toggling like 0 to 1 1 to 0. Okay. And capture mode compare mode we have to use in this, and capture mode stores CNT into the CNT means counter register into the CCR on input edge using measurement. So those are the difference how we can use the compare mode and in the capture mode. Okay. So update events occurs when a counter register reaches auto reload register and used for periodic interrupt generation time base. And when we talk about compare match, so occurs when CNT equals capture and compare register used for PWM edge generation or precise output toggling. So timer in events and interrupts. So here input capture already we discussed update event and capture match, and then talk about input capture on single edge. CNT is copied into CCR time stamp and used for frequency and pulse width measurement. Direct memory access, how we can do that? Trigger support. This is option basically update CCR and AAR and without CPU for fast waveform generation. So if you use the direct memory access, it will be fast to generate the waveform. Common timer modes, time-based periodic interrupt mode, fixed periodic tick. Like based on the one, we can decide what is the time, 1 millisecond or 10 millisecond. Accordingly, it will be repeat. And using control loop, sensor sampling and scheduling. So by this also we can timer mode. We can use actually periodic or time based. So output compare mode. In case of toggle set reset output pin or compare on compare match. Used for precise pulses and square wave generation. And in this case of pulse width modulation mode, generate duty cycle control waveform. So here basically on time and what is the on time and divided by the T on plus T off. This is a complete time basically. So we have to divide by. So each for generally PWM to be used in motor control like speed, dimming or power control. So in this in BLDC motor, like so PWM is frequently used actually. So common timer modes, time base. This is already we discussed. I just write down here in one slides. So pulse width modulator we already discussed. Generate duty cycle control waveform used for motor speed, and dimming like LED light we can do. How much time it should be on. And input capture mode, measured period, frequency, and pulse width. Used in encoders, speed sensor, and ultrasonic timing. So types of timers overview. Now here I'm just stating the like various timers being used. General purpose timer is called in short GPT. This use delays, periodic interrupts, and simple timing. Generally frequently used as such called general purpose. Capture timing timer. This is called frequency of pulse width measurement from external signals. And pulse width modulation, of course, already discussed. Timer waveform generation from for control outputs. So it is used in the motor control. Watchdog timer reset system if software hangs. Some glitches there in software, then that time will reset the system. Watchdog timer. And real time clock maintains real date and time with the low power. Okay. And system tick timer. System tick like real time operating system tick source. Okay. So let us illustrate the like timers in details. So general purpose timer, what it does basically, periodic interrupt generation, time based, periodic, non-blocking delays using compare events, basic time measurement like stopwatch will be used. So like that is one form of the general purpose timer. And typical what is the features of this general purpose timer? This is up counting and down counting, center aligned counting, multiple channels, multiple CCR registers, optional PWM support in many MCUs. So typical use like blinking LED without delay loop. So this to be considered the channel purpose timer, and like 1 kHz control loop timing and periodic sensor sampling. So capture timer more details like okay. Now we proceed move on to the other different types of timer. Now we discuss general purpose. Now we move on to the capture timer. So what is measures? It measures signal period or frequency, pulse width and duty cycle, what time is on and how much time period. Okay, this is a T on, this is a T off. Total is a T, is a T on plus T off. Time between two edges, event time. So like two edges we can see. Okay, when event timing basically. So capture timing, how it works? A rising edge, like the rising edge, sent into capture and capture register. On next rising edge, store CNT again. So like that it will store this. And difference gives period in ticks. Got it? This difference giving the period. So what is the application there to be used? This to be used in the find out the like speed revolution per minute, and encoder input timing, encoder input timing. We can also find like encoder sensor data there, how timing it gets updated. So what's the frequency? This kind of things we can find out. And ultrasonic echoing timing, we can also use this. Radio control receiver pulse measurement, here we also use. Now we will move on the pulse width modulation timer. This is frequently used output waveform. Uh, Here output waveform is like fixed frequency with variable duty cycle. So like here you can see this like our fixed frequency. This is time period t, and frequency will be 1 by f, let us say. And here on time will change always. Okay, based on the on time we get the our duties. Okay, so d is equal to t on by total time t. So let us say t on into f. This is dimensionless basically. Okay, so duty cycle controls average power delivered to load. So based on the our t on time, accordingly our power will be delivered to load side. So main parameters of PWM, frequency set mainly by auto reload register. So this will be done by the auto reload register and Prescaler Register. Okay, and duty cycle set by compare register. Okay, so there's a various register to be used in this case. So frequency is set by the auto reload register and Prescaler register, and duty cycle set by the capture and compare register. Okay, so key relation is equal to how we decide the frequency of PWM. Like let us say this is a frequency of clock divided by PSC plus 1. This is a prescaler counter plus 1. This is auto reload register plus 1. This way we can decide by, and this approximate duty cycle duty ratio, duty vector we can say CCR by AR plus 1. Because this CCR, this one you can see this one actually. Let us I already discussed on top of. You can see this one. This f clock by a PSC plus 1. So based on that relation we can achieve. Okay, so here already discussed this one. Yeah, application. Now we focus on application. So application like motor control already discussed, like speed control or torque control. So here we need to PWM is being used, and for control the speed and light emitting diode dimming, like dimming. Here we also use the PWM. So based on the on time, our dimming will be intensity will be lower, higher like that. Okay. So of course this is like a kind of switch mode power supply. So MOSFET or other switches, I mean semiconductor switch to be required for this servo pulse generation. Okay, so this is a kind of servo pulse. So Watchdog timer, more details. Proper safety mechanism to recover from software hang. Ensure safety does not stay stuck forever. Okay. So working like Watchdog timer. So this to be used looks like a safety mechanism. to recover from software hang. Whenever software hangs, some glitch is there, you can reset it. Okay. And working watchdog counts down in hardware. This start counts down, and software must refresh it before timeout. So before it should be refreshed before time passed. It should refresh. Otherwise, it gets started. If not refresh, then we our watchdog timer to be inactive and reset or interrupt. Okay. So watchdog timer is like safety mechanism to recover from software hang and ensure system does not stay stop forever. This is ensure basically, and working watchdog counts down in hardware. Software must refresh into it before timeout. If not refresh, then reset or interrupt. So typically causes of hang. Infinite loop typically causes of hang. Sometimes like infinite loop there. Then it's software is get hang. Yeah, deadlock, stack overflow, memory corruption. So this like a various causes how software get hanged: infinite loop, deadlock, stack overflow, and memory corruption. Okay. So this is very important, like typically causes of hanger. There are other various causes also up there, but right now we just illustrated this one. You can also write it down in comments what's the different types of, I mean, hang causes actually, software hang causes. Yeah. So best practice replace only after system health checks pass. So that's important. So best ever health checks all get passed, then only refresh to be done. And log reset region after reboot. Yeah, this is also important. Log region reset region after reboot. So real time clock. So RTC more details. Purpose. Now we move on the real time clock. That's a very important. And purpose keep real date in real time even when MCU microcontroller is sleeping mode also in sleeping. So real date and time also. Okay. Yeah. So real time clock. So purpose keep real date and time even when MCU is sleeping. Typically clock like 32.768 kHz crystal. This generally used for the low power and stable. So typical clock 32.768 kHz crystal and feature alarms wake up at a specific time. Periodic backup interrupts and backup battery domain also there. So application data logging, timestamps we can do like we want to sensor data. So for this we require the data timestamp also. Okay. So that's why this is important. So real time data can be fetched, and this also to be useful in schedule the backups for lower power device. Of course, power for this is limited, so low power application can be used for this. Okay, now we move on the system tick timer. So more details found in RM Cortex-M microcontroller units. This is the embedded type of microcontroller version we can say actually. Okay, so this found in the this type of ARM Cortex-M microcontroller units. So purpose provides system time based on real time operating system RTOS used for task delays, timeouts, time slicing. Okay. So design node smaller tick period equal to higher resolution but higher CPU overhead. Okay. So it require more computation actually in CPU. Larger tick period, lower overhead but less time resolution. Okay. So tick frequency code timer mathematics. Tick frequency is equal to F clock by PSC plus 1. Prescaler counter plus 1. So code timer mathematics tick frequency already we know. Update frequency f update is equal to f tick by ARR plus 1. So whatever we found here, so this to be there. So you can find basically f c clock by PSC plus 1 and ARR plus 1. And tick period is equal to, of course, tick period is equal to, tick period, yes. 1 by, we can, this is inversely reciprocal of the frequency tick. Okay. So like example, 1 millisecond interrupt, given clock frequency like 48 megahertz. So choose Prescaler Register 47 and tick frequency become 1 megahertz, 1 microsecond per tick. Okay. So this like divide by 48 by 1 plus 47 Prescaler counter register, sorry, and it will be 1 actually. Okay. And choose auto reload register 999. Okay. And result periodic entered every 1 millisecond. Okay. So what's the summary? Timers are hardware counters inside microcontroller units. So this is hardware counters inside the microcontroller units. Key register we are using here. Prescaler register set time speed, tick speed, and counter register store current count. Auto reload register sets period and frequency, and capture and compare register sets compare PWM or restore capture measurement. Okay. And timer times like GPT, general purpose timer, capture, PWM, double watchdog timer, RTC, real time, and system tick. Master time math, and you can configure like we can configure any innovative time system whenever we know this actually. So based on our application, we can do actually. Yeah. So which microcontroller unit are you using actually? STM32, ABR, PIC, and ESP32. So next topic, I think we will discuss more advanced PWM, edge aligned or versus center aligned, input capture noise, filtering or debouncing, timer interrupt jitter or latency, RTOS timing or tick list mode. Okay, so I think we just discuss fundamentals, not like more dive into in this. So that's all. And if you any doubt, please do comments, and we will try to clear your doubts. Okay, so that's all.